Welcome to this explainer, where we're going to completely demystify the ultimate blueprint of the physical world. Today we're taking you on a really fascinating, highly structured journey. We're going to start way down in the microscopic, almost magical world of quantum mechanics and zoom all the way out to the massive, macroscopic organization of the periodic table.
Right off the bat, let's dive in by asking the fundamental question that literally drove centuries of scientific discovery. How exactly do these unseen strange quantum rules build everything around us? I mean, it's a massive question, right? But by mapping it out step by step, the answers actually become incredibly clear.
We're taking a definitive micro to macro approach today. Here is our roadmap. We'll start with the subatomic foundation, move into the quantum revolution, and then map the electron. After that, we'll cover the rules of engagement, scale up to the periodic architecture, and finally wrap up with the macro trends of matter.
Okay, Section 1. The subatomic foundation, establishing the building blocks.
So manipulating the most basic building blocks, specifically protons and neutrons, actually changes an atom's nuclear identity. It's like tweaking a recipe. Isotopes share the exact same atomic number, but they differ in mass, kind of like carbon-12 and carbon-13. Isobars, well, they flip that around entirely. They have different atomic numbers, but the exact same mass number, like argon and calcium-40. And then you have isotones, which just share the exact same number of neutrons. Ultimately, it all comes down to the math of the nucleus.
Moving on to Section 2, the quantum revolution, shifting the paradigm. To really understand why the periodic table is shaped the way it is, we first have to wrap our heads around the incredibly strange quantum rules governing those subatomic building blocks. You see, physics underwent this massive revolution when we realized that radiation doesn't just act as a wave, which is what we thought back in the 17th century. It actually also behaves as a particle, traveling in these discrete little packets called photons. And this dual nature, it perfectly set the stage for Werner Heisenberg. He mathematically proved that it is absolutely impossible to perfectly map a microscopic particle's exact position and its momentum simultaneously. Basically, if you know exactly where it is, you literally don't know where it's going.
Because of this fundamental uncertainty, older models like Niels Bohr's famous concept of electrons traveling in these fixed stationary planetary orbits, well, they completely fell apart when applied to multi-electron atoms. Bohr's model just couldn't account for things like the splitting of spectral lines in magnetic or electric fields. So this forced scientists back to the drawing board to rethink the entire architecture, ultimately finding a new mathematical solution in the form of wave mechanics.
So, here's the major shift. Instead of drawing exact planetary orbits, we now use these highly complex wave equations to calculate probability density. We are no longer looking for a distinct dot on a circle, we're looking at a fuzzy cloud. And these clouds highlight the exact spatial region where an electron is more than 95% likely to be found.
Which brings us to Section 3. Mapping the electron, the quantum address system.
Now you might be wondering, how do we actually locate these electrons in a fuzzy cloud? Well, they don't just exist randomly. They actually have a highly specific quantum address made up of 4 unique numbers. First up, the principal number tells us the distance and energy. Second, the azimuthal number gives us the subshell type and its shape. Third, the magnetic number pinpoints the exact orbital orientation in 3D space. And finally, the spin number dictates the electron's axial motion, whether it's spinning clockwise or anti-clockwise.
And what's really cool is how these purely mathematical quantum numbers transform into actual, physical, 3D architectural shapes. You get the spherical s orbital, the dumbbell-shaped p, the double dumbbell d, and the highly complex f orbital. But crucially, this geometry includes nodes. These are literally empty spaces where the probability of finding an electron is exactly 0, no exceptions.
Let's look at Section 4, the rules of engagement, strict allocation constraints.
So think of these next concepts as strict cosmic zoning laws. The Aufbau principle, the Pauli exclusion principle, and Hund's rule govern exactly how electrons populate those spatial orbitals we just talked about, and you simply cannot break these 3 rules.
Fascinatingly, the Aufbau principle acts like a very strict energy ladder. Basically, electrons are fundamentally lazy. They always want the absolute lowest energy state possible. Because of how the math works out, an electron will actually jump in and fill the 4s orbital before it fills the 3d orbital, simply because 4s has a lower overall energy value. They always fill from the bottom up, step by step. And once an electron is on a specific step of that ladder, the other 2 rules immediately kick in. The Pauli exclusion principle ensures that no more than 2 electrons can ever share a single orbital space, and if they do share it, they must have opposite spins. Meanwhile,
Hund's rule mandates that electrons have to spread out into empty equal energy rooms first, before they even think about pairing up. They highly prefer single occupancy with parallel spins for as long as mathematically possible.
Section 5. The periodic architecture. Zooming out to macro. So, the quest to macro-organize the elements didn't happen overnight. It evolved over centuries. It started out with simple mathematical triads back in the early 1800s, moved through theories of repeating octaves, and progressed all the way to Dmitri Mendeleev's famous table based on atomic mass. But the real breakthrough? That finally culminated in the modern era with a brilliant scientist named Henry Moseley. Moseley's breakthrough was a total game-changer. He proved mathematically, using X-ray frequencies, that atomic number, literally just the number of protons and not atomic mass, is the true fundamental property that dictates the periodic law. And this discovery completely fixed all the frustrating anomalies in Mendeleev's earlier mass-based table.
Now, because of that quantum address system we mapped out earlier, Moseley's modern periodic table naturally and beautifully divides into 4 distinct architectural blocks: the S, P, D, and F blocks. The shape of the periodic table we all recognize? It isn't just arbitrary. It's a direct macroscopic reflection of subshells filling up with electrons according to Aufbau, Pauli, and Hund. You've got the S block on the left, the P block on the right, the transition metals making up the D block in the middle, and those inner transition elements down at the bottom, that's your F block.
And our final section, 6. Macro trends of matter. The master overlay.
Once we have all this structured, every single trend across the table is governed by a fundamental invisible tug-of-war. Horizontal trends, when you move left to right, are driven by an increasing effective nuclear charge. The nucleus is getting stronger, which pulls the electrons in much tighter. But vertical trends, moving top to bottom, are driven by the shielding effect of adding entirely new orbits, which actually pushes the outermost electrons further away.
So if we look at this matrix, it acts as your ultimate cheat sheet for how properties shift. Notice how atomic radius perfectly mirrors the metallic character of the elements across the board. As you move across a period from left to right, the atomic radius decreases, and so does the metallic character. But as you move down a group, they both increase. It is just a wonderfully elegant interlocking system.
Speaking of radius, we obviously can't just take a tiny ruler to a fuzzy electron cloud, right? We have to measure the distance between atomic nuclei, and this means the radius actually changes depending entirely on the type of bond. We see a really tight, shared covalent radius, a slightly different metallic crystal radius, and a much wider van der Waals radius between non-bonded molecules. And interestingly enough, losing an electron makes a cation noticeably smaller than its parent atom, while gaining an electron causes electron repulsion, drastically expanding the anion.
We have scaled all the way from completely invisible probabilities to the absolute blueprint of matter, charting exactly how quantum numbers dictate the very shape of the elements we interact with every single day. But, it leaves us with one thrilling final thought. If quantum mechanics perfectly dictates everything on this table, what unseen rules are shaping the dark, undiscovered corners of our universe? Thank you so much for exploring this with me today in this explainer, and definitely keep questioning the mechanics of the world around you.